Now let us discuss the applications of steric effect. Now here is one example, that is picryl iodide. It contains 3 nitro groups connected to a benzene ring, and then there is one iodine atom. Now this iodine group is spherical and the nitro group is planar, in the sense all the atoms, that is nitrogen, oxygen and this oxygen, will lie on this paper. So also this nitrogen, this oxygen and this oxygen will lie on this paper if the iodine group were absent. Iodine is a large atom, a bigger atom, a bulky atom we can say. So when the nitro group is planar with the benzene ring, then this iodine can exert its steric effect. Then all these groups, that is iodine, nitro group and this nitro group, can rotate around this single bond, around this single bond, around this single bond. Rotation of iodine will not create any decrease in steric effect, whereas nitro group can rotate such that this nitro group is in a plane perpendicular to the plane of the benzene ring. So the plane of the benzene ring is like this and the nitro group will be in this direction. So this is the plane of the nitro group. So also this nitro group, due to steric repulsion, will assume a plane perpendicular to the plane of the ring. Now if the nitro groups are planar, then the p orbitals which form the pi bond in the benzene ring and the p orbital which form the pi bond here, also here. Now all these pi bonds will be parallel to each other, or all the p orbitals which form such pi bonds in benzene as well as in the nitro group will be oriented parallel to each other. Then only the minus mesomeric effect of nitro group can operate. If this nitro group is in a plane perpendicular to the plane of the benzene ring, then the p orbitals of benzene ring and the p orbitals of nitro group which form the pi bonds are mutually perpendicular, they are not parallel, so they cannot overlap. So minus m of nitro group is prevented in both these cases. Now the para-nitro group, these are ortho positions, their steric effect is present. So nitro group comes in a plane perpendicular to the plane of the benzene ring, so that steric repulsion is, or a steric hindrance, we call another name, that is steric hindrance. So steric repulsion or steric hindrance is absent when the nitro groups in the ortho positions assume a plane perpendicular to the plane of the benzene ring. Then minus some effect of these nitro groups are absent, whereas the para-nitro group can show minus m effect, so minus m is possible here. Now the lone pair of iodine will be coming over here. Simultaneously this bond will be shifting in this direction, this bond will be shifting in this direction, and this pi bond here will be shifting over oxygen, and we get a canonical structure in which the CN bond is having double bond character, whereas here the CN bond will be having single bond character. So measurement of CN bond lengths in this molecule by experimental studies have shown that for the para-nitro group the CN bond length is 1.35 angstrom, whereas for ortho-nitro groups, the CN bond length is 1.45 angstrom. And the CN bond length, normal CN bond length, as in a primary amine, for example CH3 NH2. Here the carbon to nitrogen bond length is 1.47 angstrom. And here, in the case of the orthoisomer, even though mesomeric effect is absent, the bond length is slightly less, 1.45 angstrom, because in the normal CN bond length measured in this molecule, this carbon is sp3 hybridized and this nitrogen is sp3 hybridized. Now, here this CN bond length is slightly shorter than the CN bond length because the nitrogen here is sp2 hybridized and the carbon here is sp2 hybridized. So sp2 hybridized carbon will possess more s character and less directional character. So an sp2 hybridized orbital will be shorter than an sp3 hybridized orbital. So the bond length is slightly less than this value. So that is one application of steric effect. Now steric effect can affect the acidity of benzoic acid. For benzoic acid, we have the pK value 4.17. Now if there is an orthomethyl group in benzoic acid, so this is a derivative of benzoic acid. There is an orthomethyl group. It is called orthotoluic acid. And there this methyl group is having a pyramidal shape, so that the electron cloud will be nearly spherical in the form of a cone, and the COOH group is nearly planar because the carbon and oxygen atoms lie in the same plane, because this carbon is sp2 hybridized and this oxygen is sp3 hybridized, so OH bond will be directed at an angle of 109 degree in the downward direction. So when this COH group is planar, it can sterically interact with the methyl group. So there is steric repulsion between methyl group and the COH group when the COH group is planar. So to avoid repulsion, this methyl group can rotate about this single bond. So also this COH group can rotate about this single bond. But rotation of methyl group will not cause any decrease in steric repulsion because it is somewhat symmetrical. So COH group can rotate in a plane perpendicular to or nearly perpendicular to the plane of the benzene ring. Now this is the plane of the benzene ring and this is the plane of the COH group. The CO bond will be directed in this direction and OH will be directed in this direction. Another orientation possible is CO directing in this direction and OH in this direction. Now this is more convenient because this OH bond in this case will be interacting with the CH3 group. So we can adopt this particular orientation of this structure. Now here what happens is that the pi bonds in benzene ring and the pi bond in the COH group are not mutually parallel. This pi bond here is perpendicular to the pi bond here. So the parallel nature of the pi bonds are now not possible, so that mesomeric effect cannot operate. Mesomeric effect can operate only when the COH group is planar with the benzene ring, or the COH group and the benzene ring are in the same plane. So when the COH group rotates, the p orbitals of the C double bond O system, the pi bond system are not parallel to the p orbitals in the pi bonds of the benzene ring. So mesomeric transfer of electron density from the ring to COH group is prevented. When electron transfer by minus EM effect of the COH is prevented, then electron density in the COH group decreases, so that electron density around the oxygen atom of the OH group decreases, so that this oxygen will be having a higher tendency to take up the electron pair in the OH bond, making it acidic. So we can say this orthotoluic acid is a stronger acid than benzoic acid, and experimentally it is found that it is having only a lower pK value of 3.91. So lower pK value indicates higher acid strength. Now if that is the only case, electronic case, then you would expect the acidity of orthotoluic acid and formic acid nearly equal. But there is a slightly higher pK value for orthotoluic acid, and there we come across what is called a hyperconjugation occurring in this manner. So that this carbon atom gains a negative charge due to hyperconjugation. Now this methyl group can induce a plus A effect, so that this carbon can get a delta negative charge. So also this carbon can get a delta negative charge, but that negative charge, delta negative charge created here is counteracted by the minus I effect of the phenyl group. This phenyl group, due to presence of unsaturated carbon, 6 unsaturated carbons, excluding this one we have 5 unsaturated carbons, excluding this carbon 1. So due to the presence of excess unsaturated carbons, the minus A effect of benzene ring can operate, so that the small plus A effect of this methyl group can be nullified. Then the only effect remaining is hyperconjugation, which creates a negative charge. So this negative charge pushes the electron pair towards this carbon, and that is an inductive mechanism, so that electron density is pushed towards the ring by action of hyperconjugation. So this slight electron density pushing towards the carboxylic acid group makes the electron density of oxygen atom in OH group slightly higher than that in formic acid, so that this oxygen atom in orthotoluic acid will be slightly less electron attracting than the oxygen atom of formic acid. So the OH bond in orthotoluic acid, the oxygen atom will attract the electron pair between oxygen and hydrogen slightly less than the attraction of the oxygen atom for the electron pair in the OH bond in formic acid, and that is again due to hyperconjugation. So the pK value of orthotoluic acid is slightly higher than that of formic acid, and that is mainly due to hyperconjugation. Now in paratoluic acid there is no steric effect, so that plus some effect of benzene ring or minus some effect of the CH group is present, and also there is hyperconjugation involving the 3 CH bonds, so additional electron donation to the carboxylic acid group by hyperconjugation and minus sum of CH. Both these factors, electronic effects, increase the electron density around the oxygen atom in the OH group, so there is a lesser tendency to take up electron pair in the OH bond, making the H free as H positive, so that the removal of H as H positive is made difficult, and hence we say paratoluic acid this is orthotoluic acid and this is paratoluic acid. Paratoluic acid is having a lower acid strength or a higher pK value, and that pK value is higher than that of benzoic acid, and it is 4.37, whereas for benzoic acid it is 4.17. Now that much about steric effect. Now we come to another important effect. It is hydrogen bonding or hydrogen bond. Now hydrogen bond is formed by mainly three most electronegative atoms, that is fluorine, oxygen and nitrogen. The electronegativity of fluorine is 4, for oxygen it is 3.5, for nitrogen it is 3. Now hydrogen bonding is the bonding between the hydrogen atom of a polar bond and another electronegative atom like fluorine, oxygen and nitrogen. Now consider hydrogen fluoride molecule. The hydrogen possesses a delta positive charge and fluorine possesses a delta negative charge. Due to the electronegativity difference for hydrogen, the electronegativity for hydrogen is 2.1 and for fluorine it is 4. So there is a large difference in electronegativity, and hence the HF bond is polar with a delta positive charge over hydrogen and a delta negative charge over fluorine. Now this delta negative fluorine can form a weak bond with the delta positive H of another hydrogen chloride molecule. And the fluorine atom of the second molecule can form a weak bond with H of another HF, and so we get a long chain of molecules. Now this is reflected in the boiling point of hydrogen halides. For hydrogen chloride, the boiling point is minus 85 degrees Celsius, whereas for hydrogen chloride, the boiling point is 19.5, to much higher value than minus 85, and this much higher value of HF as the boiling point is due to, we can say, hydrogen bonding. Now hydrogen bonding causes association of molecules. Association. See, in the gaseous state, molecules are far apart, whereas in the liquid state, molecules come closer. These molecules come closer and form the liquid state. So this is a type of association. So molecules are associated, coming closer, and in the solid state they are coming very close to each other. So we get a packed structure like this. So molecular association due to hydrogen bonding causes a substance to exist in the liquid state, and that feature is especially given by water, H2O. Water is a liquid, and that is solely due to hydrogen bonding, where one water molecule, HOH, can form a hydrogen bond here with oxygen of another water molecule. Then this hydrogen can form hydrogen bond with another water molecule. Now the lone pair over the oxygen atoms, there are two lone pairs. They can form weak hydrogen bond with the hydrogen atom of another molecule, and so two more hydrogen bonds are possible here and two hydrogen bonds here, so that a water molecule can form a total of 4 hydrogen bonds. So such a vast hydrogen bond structure of water. So H2O exists as a liquid, whereas its higher member, that is H2S, is a gas. So H2O is a liquid and H2S is a gas, and this is mainly due to the hydrogen bonding in the case of water molecules. We say hydrogen bonding causes association of molecules to get into the liquid phase. Now in the case of ammonia, the boiling point is very low, 33.42. In ammonia, the hydrogen bonds are very weak, and this may be due to the small electronegativity difference For nitrogen, the electronegativity is 3, and for hydrogen it is 2.1. So a difference of about 0.9. So the polarity of the bond is very low. So the ammonia molecule can form only weak hydrogen bonds, so that association is less, so ammonia exists at room temperature as a gas. Now the hydrogen bonded structure is said to be a resonance hybrid. The OH bond partially getting bonded with the oxygen atom. This is the hydrogen bond. Now this bond may partially shift in this direction. So partial bond shift here occurs, and this bond becomes a strong bond, strong covalent bond, and this bond becomes a partial bond. Now the reverse can occur to give back this structure. So these two are the canonical structures, or hydrogen bonded structure is a resonance hybrid. Now the hydrogen bond energy is nearly 6 kilocalories per mole. So it may differ depending on the nature of the molecule. In ammonia, the energy may be very low. In water and HF, their hydrogen bonding energies are high, and the average value is about 6 kilocalories per mole. And the hydrogen bond is called the strongest among the weakest bonds. There are weaker bonds like van der Waals bonds, ion dipole bonds, dipole bonds, London dispersion bonds or London dispersion forces. Then dipole induced dipole bonds are there. So all these are weak bonds, and hydrogen bond is also a weak bond, but it is the strongest bond among the weakest bonds. Now there are two types of hydrogen bondings. One is called intermolecular hydrogen bonding, and the other is called intramolecular hydrogen bonding. So intermolecular means between two molecules, and intramolecular means within the same molecule. Now organic molecules like orthohydroxybenzaldehyde and orthonitrophenol can show intramolecular hydrogen bonding. Now this CO group here is polar. There is a delta positive charge here and a delta negative charge. OH bond is polar, delta negative on oxygen and delta positive on hydrogen. So these two charged atoms, oxygen and hydrogen, can form a weak bond, that is hydrogen bonds. So that orthohydroxybenzaldehyde acts as a single unit. Similarly, orthonitrophenol, the OH bond is polar with a delta negative and delta positive charge. NO bond is having a negative charge over oxygen atom, so there is weak bonding between oxygen and hydrogen, that is hydrogen bond is formed. So orthonitrophenol also act as a single bond, a single unit. Now they are less soluble in water because they cannot form hydrogen bond with the water. The hydrogen bond is formed within the molecule, so that they are less soluble in water. And when a solution containing this component, that is orthohydroxybenzaldehyde or orthonitrophenol, when steam is passed through the solution, these molecules will come along with the steam. We say these compounds are steam volatile, so they will come along with the steam. And if we condense the steam, if we cool the steam, then we get two liquid layers. One is that of the organic compound, it may be orthohydroxybenzaldehyde or orthonitrophenol, and the other layer is water, and we can separate these two layers using a apparatus called separating funnel. So separation of these components, steam volatile components, we say steam volatile compounds, are possible by steam distillation. Then hydrogen bonding can affect acid strengths. Here the acid shown is orthofluorobenzoic acid, there is fluorine connected in the ortho position. So it is orthofluorobenzoic acid, and fluorine can form hydrogen bond with the OH group. So there is no steric effect because fluorine is a small atom. So this is a COH group can be in the same plane as the plane of the benzene ring. There is a bonding between H and F, and this hydrogen bond amounts to an energy of about 6 kilocalories per mole. So we have to spend such an amount of energy, that is 6 kilocalories per mole, to break this bond, and also to break the OH bond into H positive. Energy is needed, so that removal of H as H positive is made difficult by hydrogen bonding, so that its pK value will be higher. Then when we consider orthochlorobenzoic acid, there is no hydrogen bonding, so removal of H as H positive is made easy in this case than compared to this orthofluorobenzoic acid. So when we compare orthofluorobenzoic acid and orthochlorobenzoic acid, orthofluorobenzoic acid has a higher pK value or lower acid strength because we have to break the hydrogen bond formed between fluorine and H atom in the OH bonds. So orthofluorobenzoic acid is a weaker acid, and the main reason is hydrogen bonding. Fluorine cannot form hydrogen bond. Now coming to another example, that is orthohydroxybenzoic acid. Orthohydroxybenzoic acid is also known as salicylic acid. Now this hydroxy group is not so sufficiently large enough to exert steric repulsion, because oxygen is a small atom and hydrogen being a still smaller atom. What happens is that when the OH group eliminates H as H positive, the negative charge over oxygen atom can form hydrogen bond with the OH group, the H atom of the OH group. So this ion is made more stable because during hydrogen bond formation 6 kilocalories of energy per mole is liberated. When energy is liberated, the energy of the system decreases and stability increases, so that during hydrogen bond formation the system becomes more stable, and if the system is more stable, then formation of such a system is made rapid, means more of this ion is made, and when more ions are made, more H positive ions are liberated, so that salicylic acid is having a pK value of 2.98, so that the acid strength is increased in the case of salicylic acid when compared to benzoic acid, whose pK value for benzoic acid is 4.17. So compared to benzoic acid, salicylic acid is a stronger acid because its pK is 2.98, and this is due to the stabilization of the carboxylate anion by hydrogen bonding with the OH group. So the anion or conjugate base of the salicylic acid is stabilized by hydrogen bonding. Now if you are having another OH group in the other ortho position, then the CW negative group, this CW negative group, due to resonance, can produce delta negative and delta negative at the two oxygen atoms. So this is the resonance hybrid structure of carboxylate ion, where delta negative and delta negative over the two end oxygen atoms. Now when there is another OH group in the auto position, this delta negative oxygen can form hydrogen bond with one OH, and also this delta negative oxygen can form another hydrogen bond with the OH. So there is a double stabilization, we can say, so that the pK value of 2,6-dihydroxybenzoic acid is 2.3, lower than that of orthohydroxybenzoic acid, that is salicylic acid. So hydrogen bonding can stabilize the corresponding acid anion and increase the acid strength or decrease the pK value. Now coming to a detailed study of SN1 mechanism. Now we have seen that during SN1 mechanism a carbocation is formed. Now before discussing further the SN1 mechanism, let us discuss the nature of ordinary light. Ordinary light consists of an electric vector and magnetic vector. The electromagnetic radiation, which consists of one electric component and one magnetic component, or one electric wave and a magnetic wave. Now for one radiation, the electric wave will be in a plane and the magnetic wave will be in another plane perpendicular to the plane of the electric wave for a single radiation. But we cannot get a single radiation as such, we get a collection of radiations. In all these radiations, the electric vector is present in a plane perpendicular to the plane containing the magnetic vector. But the planes of different radiations will be oriented at different angles. So ordinary light consists of a collection of radiations and whose electric vectors are in different planes, and magnetic vectors are in perpendicular planes and they are also in different planes. So such a collection of ordinary light, when passed through a device called a Nicol prism, we get the coming out light as one in which all the electronic components, all the electric components, not electronic but electric components or electric vectors or electric waves are confined to one single plane. So all the electric components or electric vectors or electric waves are confined to one plane, and all the magnetic components or magnetic vectors or magnetic waves are confined to a plane perpendicular to the plane of the electric components. Such a light is called plane polarized light. So in plane polarized light, we will see only two planes, one plane containing all the electric vectors and the other plane which is perpendicular to the plane containing the electric vectors contain all the magnetic components. Now let us see what is an optically active molecule. We can simply say that an optically active molecule is a molecule in which a carbon atom is connected to four different groups, and here we have an optically active molecule where the carbon atom is connected to hydrogen, a different group that is methyl, another different group that is ethyl, and a fourth different group that is hydroxy group. Now you place a mirror in front of this molecule, you will get the image structure. Then you take this image structure and place it over the object structure. So this is the object and this is image. You take this image structure and place it over the object structure, or you take the object structure and place it over the image structure. When you are taking the image structure and placing it over the object structure, the CS3, CS2 and CS3, CS2 lie up and down. the hydrogen and hydrogen lie up and down, but the OH comes over the methyl and the methyl comes over the OH. Then we say they are not superimposable. Superimposable. So, a molecule in which the object and image structures are non-superimposable are called enantiomers. So, these object and image structures are called enantiomers. Enantiomers correspond to the same molecular formula but having different structures, and they form object and image structures which are non-superimposable. So a molecule is optically active when we can say that its image structure is non-superimposable on the object structure, and the object and image structures are called enantiomers. Now when plane polarized light, we can use an instrument called polarimeter. In a polarimeter, we can study the impact of an optically active molecule on plane polarized light. When an optically active molecule, say this one or this one, is taken in a polarimeter and plane polarized light is passed through the medium containing the optically active molecule, then the molecule rotates the plane of polarization of plane polarized light either towards the right or towards the left. So once again, when plane polarized light is passed through a medium containing an optically active molecule, the plane of polarization of plane polarized light is either rotated towards the left or towards the right. Now the plane means it can be the plane of the electric vector. So the plane of the electric vector is rotated by an optically active molecule towards the right or towards the left. And if the plane of polarization of plane polarized light is rotated by a molecule, a medium containing an optically active molecule towards the right, then it's called dextro-rotatory. And if an optically active molecule rotates the plane of polarization of plane polarized light, that is the plane containing the electrical vector, towards the left, then the molecule is said to be levo-rotatory. Levo means towards the left. So if this molecule is dextro, then this molecule will be levo. And this molecule, if rotates the plane of polarization of plane polarized light towards the right by an angle of 20 degree, then this molecule also rotates the plane of polarization of plane polarized light towards the left by an angle of 20 degree. So enantiomers will rotate the plane of polarization of plane polarized light towards the right or towards the left to an equal angle to the same extent. Now consider an SN1 reaction of an optically active molecule. Now during the formation of the carbocation, the bromine atom is getting removed as we are negative, and we get a planar carbocation. So this is a triangular structure, and it is planar means this carbon, this methyl carbon, the hydrogen and the carbon are connected to this carbon of the ethyl group, all these atoms will lie on the same plane. Now in the second step, which is the fast step, so this is slow, and in the fast step, the positive carbon can be attacked from the top or from the bottom of this triangle equally. So there is equal chance for attack of the carbocation which is planar from either side. Equal chance means if there is 50% chance for attack from the top, then there is 50% chance for attack from the bottom. So if one molecule is formed by attack from the top, the other molecule is formed by the attack from the bottom, so that we are able to get equal amounts of these two structures which are related as enantiomers. And such a mixture of enantiomers in equal amounts is called a racemic mixture. So during SN1 reaction, you always get a racemic mixture. Because there is equal chance for the attack of the carbocation from both sides. So equal amounts of enantiomers are formed. Then if 50 molecules are trying to rotate the plane of polarization of plane polarized light towards the right to an angle of say 20 degree, then the other 50 will be trying to rotate the plane of polarization of plane polarized light towards the left to an angle of 20 degrees, so that the net rotation will be 0. So equal amounts of enantiomers when formed, the mixture is called a racemic mixture, and the optical rotation of a racemic mixture is 0. There is no rotation of the plane of plane polarized light. Now this process is called racmisation, and racmisation is an evidence to SN1 mechanism. So that's all. We shall discuss the other aspects of SN1 mechanism in the next video. Thank you.